Okay, good morning. Welcome back. Happy Friday. We're just given the tests back. This is our first of 2 tests for the entire semester. We do have several more quests coming up, but only 2 tests. And this was almost a midterm. Folks generally did really well on it. If you have any specific questions, individual questions, just see me after class. I'm happy to talk to you about the test. So we move on, brand new material starting today. The first almost half of the course is largely about lines. We graphed individual lines and we talked about slopes and intercepts and contexts. And then in the last few classes, it was about graphing 2 lines, right? And talking about solving systems of equations. And the next major theme for our course is about exponents. And you can see here on our calendar, the word exponents appears today. And next class, it turns out that radicals, like square roots, is related to exponents. So radicals and more exponents and radicals. And so for the next 2 weeks, we're going to be talking about exponents and radicals. So that's the next major topic. And just word of caution, exponents and radicals is the toughest topic of this course for many people. Material gets harder and harder generally in courses. In our course, we might be nearing the peak of difficulty and things might get a little bit easier as we get to quadratics and parabolas, which you might have more familiarity with. So exponents are tough. All right, so we start on page 112. The first page of this packet is a reference sheet that we'll use in the first problem today, and it's something you're going to bring with you to future tests and quests. So we'll talk about it in just a minute. But on the top of page 112, we'll start with our summary. In this lesson, we solve word problems using the Pythagorean Theorem, and we begin our exploration of exponents by using certain rules to simplify expressions containing exponents. All right, Pythagorean Theorem, perhaps the most famous theorem in all of math. It has to do with what special shape? Not just any triangle, but kind of a triangle. A right triangle. It's got to be a triangle with a 90-degree angle in it, like this one here. And if you label the sides A, B, and C in that particular order, then A squared plus B squared equals C squared, right? This theorem has been proven hundreds of times, including one by former President James Garfield, who was an amateur mathematician, and he came up with his own proof of this theorem. Okay, so let's jump into number 2. You're shopping for a home entertainment center, and you find one at a good price. The space for the TV in the entertainment center measures 17 inches by 21 inches. That's 17 inches tall, 21 inches wide. You're wondering if your 27-inch TV will fit in the space. Let's give it a shot. First thing we're going to do is draw our rectangle for the entertainment center. And the dimensions here again are given as 17 and 21. Now that's the entertainment center. That's the space available. The TV is advertised as being 27 inches. Do you guys know what dimension is the only one advertised when you say your TV is 27 inches? Yes, corner to corner. Actually, don't know. I'm hoping they don't count like the plastic stuff around the outside. I'm hoping it's just the screen itself. You think it includes it? Well, yes, I agree. It's corner to corner, including the whole thing. Yeah, so they should just make more plastic out there, make it seem bigger. So that 27 inches is the diagonal. So let's go ahead and draw in the diagonal. Now, we're not saying that this is 27 inches. That's the space available. What we have to do is find out how long that green thing is, and then we'll compare it to the 27-inch diagonal of the TV, right? We're hoping we have enough space. Okay, but this is a rectangle, and so therefore we have a right triangle down there. So Pythagorean theorem is in play. The fancy name for the side opposite the right angle, what's it called? Hypotenuse. It's important that we call that one C in the equation. The A and B can swap, but the C has to be the hypotenuse. Maybe said better, the C has to be by itself in the equation. That's the important thing. So our equation becomes 17 squared plus 21 squared equals C squared. Yeah? Now, we are going to use the calculator, but not yet. Go to the first page, this reference sheet that I'm talking about. 17 squared is in there. If you look across the top, you'll see column headings. You want to find the one that says perfect squares or square powers. What does it say? Perfect squares. So look in the perfect squares column, go down to the number 17 in the first column, and then just look to the right of that, and you'll find 17 squared is 289. Everybody see how to read 17 squared from that page? And the reason it's going to be important for you to be able to read 17 squared on that page is on the next quest, which is admittedly several weeks away, you will not have a calculator in your hand. You will have this page. 21 squared from the page, 441. Okay, now go ahead and take out the calculator because we're going to need it when we want to finish this problem. Adding those two numbers is not hard without a calculator, but the last step, we'll use the calculator. Anyway, what do we get when we add these two? 0, 3, 730. All right. And the way to get our hands on C is to do what to both sides of that equation? Is to take the square root, right? Now this is a symbol you've seen before. I don't know that we've really used it in this class. We'll talk about it. It'll be defined in the activity today, but I think it's one you've seen already in some other math class. So we'll take the square root of both sides. The idea is that the square root of C squared is just C. You're undoing the square, so you're left just with C. And the square root of 730 is something you can type on the calculator. You'll learn how to do that in the activity if you don't know how to do it already. But can somebody tell us what the square root of 730 is? Perfect. So 27.01 inches is the length of that green diagonal. That's the available space. Will our 27-inch TV fit? Just barely. You might need to grease it a little bit to get it in there, but we have, in theory, we have just enough space to get that 27-inch TV in there. Okay, Leslie, is that all right? Questions on the Pythagorean theorem? Okay, so how do you know to use the Pythagorean theorem? The problem involves a right triangle. Any problem involving a right triangle for us is going to be the Pythagorean theorem. You won't see very many of them. We're not going to be talking about Pythagorean theorem for weeks and weeks and weeks, but if you've got a right triangle, odds are Pythagorean theorem is in play. Okay, number 3 is the main topic. We're going to talk about exponents. So just a couple of examples to make sure we're clear on definitions. 7 squared means 7 times 7. It's not so important to me that it's 49. It's just that you know what squared means. 5 to the 4th means 5 times 5 times 5 times 5. 4 copies. Yeah. Worst I ever did on a math test. It was in, I don't know when we learned exponents. I think it was 6th or 7th grade. I think it was 6th grade. And I didn't understand. And so I thought 7 squared meant 7 times 2, and I put 14. And I did that multiplication for all 20 problems on that quiz. Guess how many I got right? Actually, I did get a couple of them right. Can you imagine what, instead of 7 squared? Yeah, 2 squared would be okay. 2 times 2 is 4. Any other examples where 3 squared, would that be okay? All right, we know the answer is 9. What did I put in my misguided youth? I put 6. Yeah, that's no good. Anything to the first power. I was money on those. But I did not do well on this quiz. Okay, and then 2 to the 8th is just 2 times 2 times 2 times 8 of them, right? Okay, so we're coming down here now. So that's the easy part, the definition. Now we're going to come to some properties of exponents. These first 5 are going to be called the laws of exponents. I don't need you to know that phrase, but anyway, that's what we're going to refer to them as. The difficulty here is that there are plenty of things for exponents that seem reasonable but are false. And we need to make sure we're not applying things that are false. These 5 things are true, but there are things that are not in this table that you might want to try that just aren't going to work. Let's look at some things that are true first. Take a look at 3 to the 5th times 3 squared. 3 to the 5th means 3 times 3 times 3 times 3 times 3, 5 of them. So all I've done is written it out. 3 to the 5th is there, 5 of them. And 3 squared is 2 of them, yeah? So if I just showed you this thing and I said, hey, what is that really if you were to write it in compressed form? 3 to the 6, 7, right? 5 of them and another 2 of them, it is for sure 3 to the 7th. Okay, we just developed a shortcut. 3 to the 5th times 3 squared. What can we do with those powers to get us directly to the answer? Is add them up. That's our shortcut, right? 3 to the 5th times 3 squared is 3 to the, add them up, 7. Leslie? Because they're both a 3. Has to be both a 3. If you imagine these guys here were 4s, and I say, hey, can you write that as a single exponent? No, because it's not just a single number. Good call. Okay, so that's our shortcut there. But one thing that is tempting and is wrong is to take those guys and say, oh, I see a multiplication, so I must multiply the exponents, 3 to the 10, which isn't right. There's for sure, there's 7 of those 3s. Okay, so there's the property in general. X to a power times x to another power, you add the powers. But as Leslie says, it's got to be the same x. Okay, division is something similar. Let's take a look here. 3 to the 5th over 3 squared. You write out 5 3s on top. You write out 2 3s on the bottom. You cross off, right? We can cancel here because we've got lots of multiplication. So cross off, cross off, cross off, cross off. How many 3s are left? 3 of them. Is there something you could have recognized about the powers, the 5 and the 2, to know without writing all this out that there are going to be 3 of them left? It is the division. What can we do with the 5 and the 2 to get the 3 remaining is subtract, right? And it makes sense because there were 5 and there were 2 and you cross off the 2 and whatever's left over by subtracting is the remaining power. So that's subtract. Emma. There is a time. Next row. Okay. So what we just saw here is that if you have x to a power divided by x to a power, you subtract them. Again, got to be the same x. One other thing, this example is not written here, but for, suppose that I gave you this, 5 to the 4 over 5 to the, I don't know, 10. Same 5. So this is our property. We get to subtract them. However, imagine these 5s all written out. Imagine 5 up on top, 4 of them, and then 10 5s on the bottom, and you cross off. How many 5s will be left over? 6. It's the same subtraction, but where will they be? They're going to be on the bottom, right? You're going to cross off all the 5s on top because there weren't as many up there. The 6 5s left over are definitely on the bottom. And so yes, it is still subtract, but you got to put them where there are more because you're thinking about writing them out and crossing them off. So wherever they will be left over is where there were more of them to start with. I got to put something on the top. It's a 1, right? So that probably is a good example just to write down is that you want to be subtracting, but you got to make sure you put them where there are more. Another option, which we'll talk about next class. Hang on one second. So Emma says, hey, I could do 4 minus 10, which is exactly what that property says. 5 to the negative 6 is correct. At this moment, we don't have a definition for a negative exponent. We will next class. But my preference is to make the exponent positive. So I always subtract in the easier order, the positive order, and I put the thing where there are more of them. We have not defined 5 to the negative 6. It doesn't involve making the thing negative. We'll see you next class. Okay, but Emma's right. I mean, 5 to the negative 6 is a perfectly good answer. But I want us to get in the habit of trying to build positive exponents when we have a choice. Okay, next example is something like this. 3 to the 5th squared. Okay, I've got a 3 to the 5th squared. Maybe I add those. Maybe it's a 7. I'm not sure. Maybe I'm supposed to take 5 and square it. Maybe that's a 25 up there. There's lots of things you could think to do, but only one thing is right. So 3 to the 5th squared. What does it really mean? Well, squaring something means write it twice, right? So 3 to the 5th times 3 to the 5th, that's squared. And then there's the first 5 of those 3s, and there's the second 5 of those 3s. So how many 3s are there? 10. And is there a shortcut you can do with the 5 and the 2 to get the right exponent of 10, as you can multiply them? And so Emma had asked, is there a time when you multiply exponents? Yep, it's right there. When you have something to a power, the whole thing to another power. You multiply those powers, okay? All right, next example is down here. Suppose that we have 3 times 4 cubed. We're just going to write this out naively in the beginning. Something cubed just means write it 3 times. So everybody agree that is 3 times 4 cubed by just writing 3 times 4, 3 times 4, 3 times 4. You can multiply in any order you want. Anybody remember the fancy word for that fact about multiplication? No? No? Starts with a C. The commutative property, which is a fancy word, says you can multiply in any order you want. And so all I'm going to do is commute the 3's to the front. So I've got my 3 3's, but just shuffled together. And then I've got my 3 4's shuffled to the back. It's just rearranging. And 3 times 3 times 3 is 3 cubed. 4 times 4 times 4 is 4 cubed. I don't care about the number. I'm looking for a general property, like what really happened here. Okay, so what happened? You had a single exponent on the outside of a multiplication, and the final answer had that exponent on both of the factors in the parentheses. So I'm going to draw this and say that that exponent comes in and distributes, but that's not the right word, so don't quote me on that. Distribute is not this, but it looks to me like the distributive property where something outside the parentheses comes in and hits everybody inside. So when I see something like this, I can take that power and, quote, distribute it to both of the factors inside. 3 cubed, 4 cubed. Is that okay? And that's just written generally in the front here. X times y to the m. Take that m, distribute it to both x and y. Similarly, for division, if you have some exponent on the outside of a fraction, you're going to take that exponent and distribute it to both. X to the m over y to the m. You can look at the justification later if you want. Okay, 5 laws of exponents, together with lots of things that look reasonable but are not true. One last thing for today, and then we'll look at the activities. Number 5, it's important that we can handle negatives and exponents together. Let's try the following without a calculator. -4 in parentheses squared, and before we do that one, I want to look at the very next example, which says -4 squared without parentheses. Now let's see if these are the same or different. Okay, -4 squared literally means -4 times itself, yes? So what is that? 16, for sure. That is positive 16. It is not negative. Now, many students look at this next example and see the same thing as the first example. They see the number -4 and they say, oh, -4 is being squared. Don't write that. Because if you write that, you're going to get the same positive 16, which is sadly not the right answer. Think about this. -4 squared is really the same as -1 times 4 squared. A negative is really just saying -1 times, right? Any negative you can imagine. It's really just -1 times something. So when we look at it that way, and we apply, Joel, you had said Pemdas before. Pemdas is that acronym for the order of operations. First parentheses, I don't see any. Then exponents, and after that multiplication division. So which one comes first here, the multiplication or the exponent? Exponent comes first. And so this is saying -1 times, the multiplication is on hold. You do the exponent, 4 squared is 16, and then you finish with the multiplication and you get -16. -16. Yeah, the only way that the exponent has enough reach to get all the way out there is if you give the exponent more power than it would normally have by putting parentheses. Yeah. So do not envision parentheses where they aren't given. This is not the same problem as the first one. If you really want to put parentheses in there, it's really that, right? It's really exponent first, slap a negative on it at the end, right? It's really, so listen to the pause here, it's really -4 squared, -16, okay? Last one puts it all together, so let's do it in pieces here. This negative is clearly just hanging out until you deal with the first part, or the parentheses part. How much is this? That is definitely positive 16. That's the first thing in the table. So what's the final answer here? -16. It is very easy to get the wrong answer by saying first, oh, hey, look, negative times negative makes what? Positive. And if you change those both to positives, then you'll think it's positive 4 squared, which is positive 16, which isn't it. And the reason you can't just cross off these two negatives and make a positive is because you have to deal with the exponent before you deal with the multiplication. That first negative sign is saying a negative 1 times. It's an implied multiplication. That's why it's so tricky. It's because we're not writing out what we really mean. We really mean negative 1 times parentheses. So it's this little kind of a shorthand like notation that mathematicians use that lead to errors if you don't know how to read it. Okay, last property for today is this guy right here. A to the 0 equals 1 for any number A other than 0. Let's try this on the calculator real quick. Any number to the 0 is 1. For example, 17 raised to the 0 power, what is it? It's 1. And there, I got a fancy pi button. Let's use that. Whoops, pi to the 0 is 1. Easiest question you'll ever find. Any number to the 0 is 1. Doesn't matter how complicated it is, right? I can put some crazy stuff in here. Here, I'll use this number e, which some of you might have seen in another math class. It's another irrational like pi, which is some long number. If I raise all of that gobbledygook to the 0, what do I get? 1. Hey, that's it. Why is 1? Yeah, good question. We are going to talk about why this property is true next class. So I'm going to ask you to trust me for 96 hours and we'll justify it on Monday, okay? But for right now, just take my word for it. Any number to the 0, we should define it to be 1. There'll be motivation for why we should make this definition on Monday. Okay, so in the first blank, 4 to the 0 equals 1. All right. 5x to the 4 over y to the 17 all to the 0 is 1. Don't be distracted by trying to apply other properties from the table on the previous page. Just anything to the 0 is 1. Negative 3r to the 0 is 1. Negative 3r to the 0 is it's not 1. It's negative 3. It's the order of operations. I'm going to put a little multiplication dot there. It's negative 3 times r to the 0. Exponents are very weak. They can't reach far. The exponent only applies to exactly what it is touching. That exponent is not strong enough to reach the 3. It's not strong enough to reach that negative sign. It is only reaching what? The r. So you deal with the r to the 0, and then you deal with the negative 3 times. So this is really saying negative 3 times r to the 0. Negative 3 times what? 1, which is negative 3. Okay, there are, I think, 3 activities coming up, so you're just going to go through them one at a time and keep turning the page until you run out of stuff to do. Raise a flag if I can help.